Okay, today we are talking about section 20.4, which deals with what's called EMF. EMF is what we'll be talking about here in just a second, but we're going to be able to calculate it. It is a number that we'll be able to find when we're given different electrode potentials. Okay, just like in our discussion yesterday, one of the redox reactions that we talked about was zinc metal reacting with copper and producing copper metal and zinc ions. Okay, and one of the things we're going to be talking about today is why does that actually occur? Okay, another way to look at it is why do these electrons transfer from a zinc atom to a copper ion, or why will it do it if you're using a voltaic cell through a circuit? So we're going to talk about this driving force that pushes electrons through an external circuit in a voltaic cell. Okay, and an easy way to look at this and think about how this actually occurs is if you think about a waterfall. In a waterfall, the water at the top of the waterfall has a very high potential energy. And then that water spontaneously falls, converts to kinetic energy. Then when it hits the bottom, it has a very low potential energy. So water having a very high potential energy spontaneously falls until it converts to kinetic energy, and then it has a low potential energy once it reaches the bottom. Okay, just like that same example, in certain substances, electrons flow spontaneously from one substance to another because they have a higher potential energy. So they're simply flowing from a position of high potential energy to a position of low potential energy. Okay, so we know that the electrons always flow from the substance that's being oxidized to the substance that's being reduced. So we know that electrons flow from the oxidation point, which is again is the anode. Remember the valve thing. From the anode to the cathode. And when that occurs, the reason that does occur is because the potential energy of that anode is higher than the potential energy of the substance at the cathode. Okay, and the way that we measure that is we measure that in volts. So whenever you see these, the unit will be in volts. Volts are actually just a joule over a coulomb, which we'll talk about more here in just a couple more sections. Okay, and so what happens here is this difference in potential energy, in this case between the zinc and the copper, that difference is basically the difference between the top of the waterfall and the bottom of the waterfall, where it just spontaneously goes from one side to the other. And this difference is what is called the EMF, or the electromotive force, but much more commonly you find it referred to as the cell potential or the E cell. Okay, E cell is measured in volts, just like how we just saw. And here's the important part here. Because the anode will always be higher than the cathode, because it's all voltaic cells occur spontaneously, we know that E cell will always have a positive value. Just like how we talked about with delta G, how we said that delta G, when it's spontaneous, is equal to a negative value. We know that KEQ is greater than 1. And we also now know that in spontaneous reactions, that E of the cell is equal to a positive value. All three of those things tell you the same thing, that the reaction spontaneously goes in the forward direction. Okay, and the way that we determine the cell potential or the electromotive force is by using each reaction is going to have a different energy associated with it. It also depends on the concentration of each reactant and then also the temperature. Now, just like with gases and equilibrium and all that and delta G, we do have standard conditions, which means basically we're taking concentration out and we're taking temperature out for now. The standard conditions are 25 degrees Celsius and 1 molar concentrations, or 1 atmosphere if it were gases. Okay, when we do have these standard conditions, just like with delta G or delta H or delta S, we do put that little degree sign up there, and that is referred to as the standard cell potential. So it's the cell potential with at standard conditions at 25 degrees Celsius, 1 atmosphere. Remember, the only time you find, a lot of times, remember with gases, and don't forget this is important, a lot of time with gases we talk about STP, which is standard temperature pressure. That is the atmosphere. The pressure is 1 atmosphere, But remember, that is the only case where the standard temperature is actually 0 degrees Celsius, not 25 degrees Celsius. So make sure that's something that you remember. In most cases with delta H, delta S, delta G, with cell potentials, the standard temperature is always 25 degrees Celsius, not 0. Okay. Okay, and so just to give you an example, the zinc copper voltaic cell has a cell potential of a positive 1.10 volts. We'll talk about how you get that number here in just a second. Okay, the way that you would see this written on the exam is here's the reaction right here, and then afterwards, just like a lot of times how we write delta H or delta G or something like that, you can also just put the standard cell potential and then just put it at the end, just like how you would for anything else. Now the problem is a lot of reactions can occur as oxidations, and obviously they can also occur as reductions. What we have to take into consideration that when we're looking at all these different possible reactions of things losing electrons, things gaining electrons, we can assign a standard potential to each individual half reaction which occurs in each half cell. And then we can use those potentials to determine the cell potential. The issue, though, is that we have, some is oxidation, some is reduction. And so the way that we do have a table for this, and this is given on the AP exam. The way that we do that is we use what's called the standard reduction potentials. Okay, notice it's not E cell, it's E for the reduction. This table only shows reductions. If it is an oxidation, then you flip the equation around to make it an oxidation. Okay, and the way that you don't actually have to, when you flip the equation, you don't have to flip the sign because of that negative sign right there. When you're finding the standard cell potential, you're taking the standard reduction potential at the cathode and you're subtracting the standard reduction potential at the anode. You do not add them together. That minus takes into account the fact that even though it is an oxidation reaction, and where it's written as a reduction, that negative sign allows us to not have to flip any signs or anything like that. It's just the cathode minus the anode. Okay, we know that at the cathode, the cathode is where reduction occurs. The anode is where oxidation occurs. So you can kind of look at it as the reduction minus the oxidation. But remember, they're always written as reductions on that table. Okay, so whenever we assign a potential or a value to these half reaction, we always write it as a reduction. You will always see them as reductions. Okay, it is on page 7. There is a list on page 791. There's a complete list of Appendix E at the back of your book. There's also a list that is given on the AP exam. That's the one I would recommend that you use just so you're familiar with it. Okay, and we can use these cell potentials to calculate the EMFs of many voltaic cells. Okay, one thing that's important to remember with KEQ and with Hess's law and with kinetics and all that, anytime you change the stoichiometry, so if you double an equation or take the half of an equation or triple an equation, that always would change KEQ, it would change delta H. In this case, if you double an equation, take the half of it, anything like that, that does not change the value of the standard reduction potential. Okay, this part, don't worry about this. We'll talk about this here in just a little bit. Okay, so for the zinc copper voltaic cell, the EMF I just told you is positive 1.10 volts. If we say that the standard reduction potential of zinc is negative 0.76, we can then calculate the standard reduction potential for the reduction of Cu2 plus to Cu. The important thing here, remember that the zinc part is going from zinc metal to zinc 2 plus, so zinc is being oxidized. So when we put that into the equation, that part goes right there because it's always the cathode minus the anode. Okay, so we have 1.10 equals the reduction potential at the cathode minus the negative 0.76. So when we solve for our answer, that becomes a positive. So we're actually going to subtract that on both sides. So for the cathode, it comes out to be 0.34 volts. And that is the standard, that is the reduction potential for copper 2 plus becoming a copper atom. Okay, so here's another one. Here's our reaction here. Using that standard reduction potential, table on page 791 in your book, given this reaction right here, we should be able to calculate the EMF or the cell potential for this reaction. Okay, so if you would at this moment pause the video, look up those values in your book, and then compare your answer to mine here in just a second. I'm waiting for you to pause it. I know you haven't paused it yet. Pause it now and do it. I'm serious. Pause it right now. All right, good job. Okay, so what we had to do, we had to first identify the half reactions that occur at each electrode, just like how we did yesterday. So it looks like we've got our chromium. That's probably going to change charges. The hydrogens and oxygens generally don't. The iodine looks like it's going from a -1 to a 0 charge. So the chromiums are changing charge. The iodines are changing charge. So our two reactions are this. Hopefully you were able to determine those two half reactions. Again, to start out, you would start out with Cr2O7. What the heck just happened? What the? That was weird. Cr2O7, 2 minus, becoming Cr2Cr3 plus, excuse me. Okay, then you balance the oxygens, balance the hydrogens, blah, blah, blah. Then we do the same thing here, balance the electrons, so our two reactions come out to be that. And then we look up those values. The first reaction has a standard reduction potential of positive 1.33. The second reaction has a standard reduction of potential of 0.54. Again, the way that we wrote it is it's written as it's going from I minus to I0 with a I2 with a 0 charge. Here it's -1. So it is losing electrons, but the way you're not going to find it that way, because remember they're always written as reductions. And so what we have to do is we have to flip our equation around. And so when we're looking for this on our standard reduction potentials, it's actually going to be I2 becoming 2 I minuses. And then the 2 electrons are going to be on this side. Okay, so that's the reaction you would look for, not the oxidation. Okay, so we have our two values. We put that into our standard cell potential equation, and we get a value of 0.79 volts. Okay, now when we look at our equation here, the more positive value of the standard reduction potential, the greater the driving force for reduction. Okay, because this is a spontaneous reaction, the cell potential at the cathode, just like math is, this value at the cathode must be greater than this value here, because we know it's spontaneous, so E cell has to be positive. For E cell to be positive, the cathode must have a higher standard reduction potential than the anode. Okay, that's what I just said. Okay, and like we just said, reactions in voltaic cells always occur spontaneously. Okay, if it doesn't occur, then it's not a voltaic cell. Okay, and we'll actually see the very last section of this chapter deals with electrolysis. Electrolysis is basically a voltaic cell that uses electricity to cause the reaction to occur. Okay, so here's an example here where they give you two reactions. You would have to look up these values for these cell potentials in Appendix E or on the equation sheet, and then compare them and determine which one's going to be oxidized and which one's going to be reduced. Okay, so for cadmium 2 plus becoming cadmium, it's negative 0.403. For tin 2 becoming tin, it's negative 0.136. So we can see that tin has a smaller or a less negative value. Since it's a less negative value, it's a bigger value. So therefore, if we're doing cathode minus anode or reduction minus oxidation, this one has to be your reduction, because if not, when you subtract those two values, you'll get a negative value. Okay, so that's our reduction. This is where our reduction is occurring. This is where our oxidation is occurring. And so we just take our cathode minus our anode, and we get that as our value. If we were to switch these and mix them up, our answer would come out to be a negative 0.267, which again can't occur because they're always spontaneous reactions. Okay, we can also use this to understand a little bit about aqueous chemistry. We know that when this reaction occurs in a single vessel, they're in direct contact with each other. They are not actually producing usable electrical work, but the driving force is the same. The potential energy is higher in the zinc than in the copper. Okay? Because the standard reduction potential of copper is more positive than zinc, then the reduction of copper by zinc is a spontaneous process. The opposite does not occur. Okay, so the more positive the value for the standard reduction potential, the greater tendency for the reactant of that half reaction to be reduced. So some common oxidizing agents, so some things that are easily reduced are the halogens. Okay, remember reduction means they're gaining electrons. So the halogens commonly have a charge of -1. So they easily gain electrons. Oxygen, O2, has a 0 charge, can gain electrons to have a -2 charge very easily. And a few of these anions here also are easily reduced. Okay, and then some common reducing agents, so some things that are easily oxidized, so things that can lose electrons. Hydrogen can easily go from a 0 charge to a +1 charge very easily, so it's losing electrons. The alkali metals can go from a 0 charge to a +1 charge very easily. And then also the heavy alkaline earth metals, calcium, strontium, and barium, can also lose electrons very easily. Okay, so looking at page 863, we should be able to rank these in order of increasing strength as oxidizing agents, so how easily they're able to be reduced. Okay, Cr2O7 has the most positive value for the standard reduction potential, so it is the most easily reduced. Silver is the lowest, so therefore the order should be like that. Okay, voltaic cell produces a cell potential, a force due to the higher potential energy. The way you can determine that difference is using the cell potential. Using the standard reduction potentials, you can find out the difference between the two. There's your review questions. There are 4 of them, so that might take you a little bit. You might want to try those tonight, and then we'll talk about them tomorrow in class.